So anodes are given three unknown half cells, 1, 2, and 3. The half reaction taking place in each half cell is given below. So we're given three half cells, X, Y, and Z, where X, Y, and Z are different metals, right? So different metals that we'll find on the reductions table, the potentials table. And this is given with the double arrow, where the double arrow means that these reactions are reversible, right? That simply means that we can go from the x2 plus 2e minus 2x, which is a reduction reaction, and that would be the fourth reaction, or we can go from x neutral to x2 plus 2e minus, which would be an oxidation reaction. So we can have a forward and we can have a reverse reaction. That's simply what our double arrows mean. So, and then so we connect half cell 1 to half cell 2, understand conditions. And what understand the conditions means is that we're gonna have under, sometimes they say STP. So this means we're gonna have the standard temperature, which is 25 degrees Celsius converted to Kelvins. Under standard concentration, which is 1 mole, 1 mole per dm cube, or just 1 m, right? And if gases are involved, we use it at pressure 1 atm. When gases are involved. Okay, so under these standard conditions, and they record cell potential E as well as the metal electrode that acted as the anode. Okay, remember what is happening at the anode? Oxidation occurs at the anode, right? We'll just put a star there. We expect oxidation to occur at the anode, firstly. And the second thing is, where oxidation occurs is where we're going to expect to see our reducing agent. And the difference between these two, oxidation is the one that becomes more positive, so it loses an electron, so loss of an electron. And the reducing agent is the one that gives away an electron, so gives away E minus. Yeah. Okay. So please note down the information, as this will be the information we'll use to answer all the questions. So this is the reaction given half cell 1 plus half cell 2 gives us 0.84, where X is our anode. Again, at our anode, we expect oxidation to occur. And we get both positive over here, so we see that both of them are spontaneous reactions, right? And what does it mean if they're both spontaneous reactions? So the spontaneous reaction is a chemical reaction that occurs on its own. And what it simply means is that it doesn't require an external input of energy, and this occurs under STP, right? Does not require external input. Okay, and another thing is that spontaneous reactions often tend to favor the formation of products. Okay, and the biggest thing is, so spontaneous reactions release energy. Well, they often release energy in the form of heat, but not always. Sometimes spontaneous reactions will absorb heat, which will make them endothermic reactions. But very often they release heat, which are exothermic reactions, but they can also absorb heat, which will be endothermic reactions. Okay, so just this information we're going to be using quite a bit on the next few slides. Okay, first question is define an anode and a reducing agent. An anode, simply put, is just the electrode where oxidation occurs. Oxidation occurs. And remember, oxidation is the loss of electrons, so we can always look at it as oil rig. Oxidation is loss. And with oxidation reactions, think of it as the electrode where the chemical species become more positive. So if you have an oxidation reaction, you expect more positive. And then a reducing agent is the substance that donates electrons in a redox reaction. Right? Substance that donates, keyword donates, electrons in a redox reaction. And because it donates these electrons, it ends up getting oxidized. So your oxidation reaction is also where your oxidation reaction is where you find your reducing agent. Always. Because it's the one that's donating. Right? Keyword donate. If it donates, it means it's giving away electrons. If it's giving away electrons, it must be becoming more positive, which associates with oxidation reactions. Okay. State the energy conversion that takes place in these cells, and the energy that occurs in these cells are in galvanic cells is specifically they take chemical energy stored within the bonds of the reactants and turn them into electrical energy that can power devices. And that's in keyword here, it says in these cells, so in galvanic cells. So that's just chemical potential energy to electrical energy. Okay. State the standard conditions under which these cells operate, and that's the question we answered initially. It was you have temperature, which is at 25 degrees Celsius, plus 273.5, and that's going to give you kelvins. You've got your concentration, which occurs at 1 mole per decimeter cubed, or we can say at 1 mole. And that just means that each liter of the solution has 1 mole of the electrolyte dissolved. And we have our gases. If we have gases, we then consider pressure, and the standard pressure that we expect is 1 atm, which is the normal atmospheric pressure. Okay. Okay. Write down the balanced chemical equation for the reaction taking place in half cell A. So first and foremost, this is the anode that's given. This is anode cell, and this is the addition of the reaction. So we have half cell 1 plus half cell 2, right? And they want us to say what is the chemical reaction that's occurring between the both of them. So half cell 1 was X2 plus aqueous plus 2E minus, giving us X solid, right, from the first part. But we're told that this is the anode, so we're going to rewrite this, and we're going to say it's then X solid, and because oxidation is occurring here, we expect this to be going in the reverse direction, right? So we expect X solid to be becoming X2 plus aqueous plus 2E minus, showing that oxidation has occurred. And half cell 2, which will stay the same as the Y3 plus, so it's going to be Y3 plus aqueous plus 3 electrons on the side, and it gives us Y solid. But they want the balanced chemical equation, so we're looking for the net ionic equation. And to get this, our electrons need to be balanced. So here we have 2 electrons, here we have 6, right? So to get an electron balance, we're going to multiply this side by 3, and here we're going to say by 2, which is going to then give us, using a different color, green, let's use orange. 3 times x will give us 3x. 3 times x2 plus will give us 3x2 plus. And 3 times 2, this will give us 6 electrons, right? 2 times y will give us 2y3 plus 3 electrons times 2 will give us 6 electrons, and we're going to end up with 2. So to get our net ionic balance, we're going to cross this one out with this because now it's 6 electrons and 6 electrons. And then we're left with our 2y3 plus aqueous plus 3x solid, which is becoming 3x2 plus aqueous plus 2y solid. Okay. And note that now, because we're looking at a reaction that's happening in one direction, we're no longer using double arrows. We're now using just a single arrow. Very important. When you have your net ionic, it ends with a single arrow in one direction. Okay. Write down the symbol of the oxidizing agent. So the oxidizing agent is the one that accepts, right? Accepts an electron. So it's the one that it takes an electron from someone and then it becomes more negative. And in this case, our oxidizing agent was, remember our full net ionic reaction, let's just have it down, was 3x plus 2y 3 plus, which was becoming 3x2 plus 2y, right? And as you can see, x went from 0 neutral to 2 cations, so this is oxidized, and this went from y3 plus to 2y neutral. That means this is reduced, meaning that y managed to get electrons from x, right? And so that means our y being our reduction means that it accepted the electrons, like we say there. Hence, our reducing agent would be y3 plus. Remember, when you're looking at your oxidizing agent and your reducing agent, you always want to look at your reactant side. And the reason is on the reactant side is where you'll find either the electron donor or the electron acceptor. Donor or the acceptor. Okay. Write down the cell notation for cell B. Standard conditions and state symbols do not need to be shown. Okay, great. So for cell B, we've got the Z because they said it's half cell 1 plus half cell 3, right? And our anode is X. So when we're writing our cell notation, we start with our oxidation, moving on the left, and on the right, we're going to see our reduction. So on the left, we've got Z, solid. We don't have to write it, so we'll just leave it. So Z, which is being oxidized to become Z plus, right? Then we put a salt bridge. It's going to separate our oxidation and our reduction. And essentially, the salt bridge is essential to allow ions to flow and maintain electrical neutrality, right? So we've got ion flow. Then we put the salt bridge and then we put our reduction, which is then our X2 plus that's being reduced to X. Okay, so that's what your notation will look like. Just write it down here to be clearer. So we've got Z being oxidized to Z plus, our salt bridge, X2 plus being reduced to X. Then, which metal X, Y, or Z is the strongest reducing agent? And the second question is which metal X, Y, or Z is the weakest reducing agent? So the strongest reducing agent is the one that loses electrons most easily. And what we saw is that in both cell A and cell B, Z is oxidized, right? So because it's oxidized in both, we'll just assume that Z is then the strongest reducing agent. Reducing. And then the weakest, so the weakest reducing agent is the one that's hardest to oxidize. And what we saw is in these experiments, Y was never oxidized, which made it the weakest. So the weakest would be Y, which was never oxidized. Weakest reducing. But in the same sense, remember, Y will also be the strongest oxidizing agent. Okay. Okay, so Ayana and Zoe now connect half cell 2 and half cell 3 under standard conditions to make cell C. Okay, so this is the new cell. And the new cell is being made by combining cell A and cell B. Right, and now we need to calculate the voltage or the cell potential of cell C. So if we remember in cell A, what we had was half cell 1 plus half cell 2, right? Which gave us 0.84. 0.84. And this included half 1 plus half 2. And then cell B, we had half cell 1 and half cell 3. So anode is equals to with 0.68, which had half 1 plus half 3. Right. And technically what we want now is these two. Right. And what we understand, very important as well, that when we're calculating the the cell potential, we still have the formula E node cell for C is equal to E node cathode minus E node anode, right? In other words, reduction minus E oxidation, or E oxidizing agent minus E reducing agent, right? So we're going to look at it both for cell 1 and cell 2. Cell A, we said half 1 and half 2. And in cell A, what we understood was that our anode was X, and X was cell 1, so this was our anode. And that would make the half cell 2 that we have the cathode. And then for cell B, V, which is half cell 3, was our anode. And half cell 1, which is X, was our cathode. Right. So let's just write. So that means for cell A, E node, cell A, if we're saying cathode minus anode, would then have been what we had initially, which was E node of our cathode, which is half cell 2, which was the Y. So we're going to say E node of Y minus our anode, which is where we had X, so minus E node. Then our cell potential again for B was again cathode minus anode, where our cathode was the X metal, so EX, right? Minus our anode, which in this case was now the Z. So let's say this is equation 1 and equation 2, A and B. And we know this is equal to 0.84, and this is given as equal to 0.68. Right. Okay, so now what we're going to do is we're going to rewrite this in a way that makes the potential of X our subject of the formula, since we see it in both cell A and cell B, right? So in cell A, we're going to end up with, because we had 0.84 is equal to EY minus EX, which is cathode minus anode, we're going to end up with, let's make EX the subject of the formula, and we'll be left with our cathode minus 0.84, and then we're going to do the same thing for cell B. And with cell B, remember this was the arrow. With cell B, this over here was reduced. With cell A, it was oxidized. So this was the cathode in cell B. With cell A, this was the anode. So with cell B, we're going to end up with EZ plus 0.68 once you rearrange it. But EX is equal to EX, right? So the cell potential for X and the cell potential for X are equal to each other, right? So this over here is equal to this over here. So we're going to equate the equations together. So what we're saying here is X is equal to X. So we're going to equate these two equations. So that means we're going to have our equation 1, 0.84, is equals to equation 2, right? But based on our previous question, we understood that Y is our weakest reducing agent, which makes it our strongest oxidizing agent. and Z is our strongest reducing agent. What this then means is that this will be reduced. So we're going to see this at the cathode. And this will be oxidized. So we're going to see this at the anode. Right. And so we say it is cathode minus anode. That means we should end up with our cathode minus our anode is equal to, we do the math here, we're going to have 0.68 plus 0.84. You do the math, your cell potential for E should then be 1.52 volts. Okay, so it's substitution. Then from there, we're going to take equation 1 and equation 2. We want to make what we have common the subject of the formula, and whatever's common between them, the answer will be the same in both. And then we're going to equate those to each other, and we're going to use that to get to this point where, using question 8.8, we agree that this is reduced and this is oxidized. And yeah, that's it. Thank you very much.